So, oops. So I'm Josh. I'm an engineering officer, and today we're going to learn about kernel pwning. So before this, I guess most of you guys have only really done like user space pwning, so just pwning user space binaries. So kernel pwning is basically what it sounds like. You're exploiting the actual kernel, or in this specific talk, we'll be looking at exploiting the Linux kernel in particular. So first off, a kernel is basically just a program that interacts directly with the hardware and provides an environment to run other programs. It also provides other services like file systems, networking, and stuff like that, but those are all abstractions. At its core, it's just supposed to interact with the hardware so that the user space programs don't have to. So basically, this is what like permissions look like. We only really use ring 0 and ring 3 for Linux, I believe. So ring 0 is basically you can access all the hardware, whereas ring 3 is basically like what all the applications can access. So yeah. So these are specific services provided by the kernel. If you haven't noticed, the kernel also handles privilege levels. So one way that like kernel exploitation is useful is because let's say you've exploited some binary and like you pop the shell on some server, right? However, you only have access to like a guest account. If you have like if it's running Linux and you have like a Linux 0-day like vulnerability sitting around, then you can just like escalate your privileges to give yourself a root shell. Yeah, you can also use it for like jailbreaking and rooting devices. So this core is just basically privilege escalation because you want to use like ring 0 stuff or like access stuff that your account doesn't have access to. So when we're attacking the actual kernel itself, the attack surfaces include like syscalls and whatnot, but one of the key or one of the like the best ways to look for like kernel vulnerabilities are in actual device drivers instead of the actual like main kernel code. Because if you think about it, think about like the actual like the main syscalls the kernel uses. Those are audited a lot and those are changed a lot. Whereas if you go after like a really old device driver, it's still running in ring 0. However, it's not audited as much and it's pretty old. So it's more likely that there's going to be a vulnerability in the device driver. And in particular for CTS, most of the Linux kernel pwn challenges are mostly just like them running an exploitable device driver that you have to pwn. Yeah, so, all right, just show of hands, who has not taken 439? Okay, so one person. Okay, so basically, the way the user space programs communicate with the kernel is through these things called syscalls. It's basically there's an assembly instruction called an interrupt, and basically the kernel provides a way. It's basically interrupts are basically there are hardware and software interrupts, and hardware interrupts are basically the hardware saying, hey, suspend like execution of your program temporarily so you can handle like something that just came up. However, we can also generate software interrupts, which is how the user space programs communicate with the kernel. They generate an interrupt, which is syscall 1. Then they provide like some information on a stack and some registers, and the kernel will handle that syscall depending on like the arguments and stuff. These are how like a program asks a kernel to like perform read or write like calls, or like communicating over a network or something. And then IOCTO is a specific syscall for communicating with a device. So let's say you have like some floppy disk drive. In Linux specifically, those devices are in the /dev folder. Actually, let me show you. So go to like your /dev folder, you see all these devices, right? So ignoring like these CTYs and stuff. Do I have any? So I guess, yeah. So like these are like some USB device starters. So like how you actually interact with those hardware devices is there's a syscall called ioctls, and they basically provide an interface for you to actually communicate with the underlying device starters that control these files. Yeah. Yeah. So basically, these are how syscalls work. This should be a bit of a review if you've went to 439, but in any case, basically, you just like you're calling the read syscall in the user space program. So you supply these three arguments: the number of bytes, the buffer to read into, and the file descriptor, which is, and then you call the read like actual library, the standard library read, and that standard library read function has a specific thing at the end, which basically it traps into a kernel through an interrupt and puts the syscall number in the register. And when the kernel intercepts that interrupt, it'll handle the specific syscall based on the number in the register. You can set this up however you want. However, for Linux, there's a specific way to do it, and the kernel will handle the syscall depending on like what it is. Oh yeah, and then after that, and the way the kernel space returns back into user space is there's this iret instruction. Like he calls swap. You have to swap some like segment registers because the kernel's address space is in a different thing, and then you have to. It's here. Oops, that's not it. Yeah, so you need. It's in production mode. Okay, so yeah, you need to supply. Basically, how the kernel returns back to the program is it basically uses iret instruction, which switches the processor back to ring 3, and it also switches the instruction pointer back into the user space program that was just calling this call back to the code segment, the user space code segment, and then there's other things. Yeah, E flags and some other stuff. But yeah, those are like basically those stuff are on the stack when you call iret. So like basic user space exploit mitigations, the kernel also has some exploit mitigations. There's more than this, but these are like the basic ones. So SMMEP is basically it'll generate a page if SMMP is supplied. If you're running the processor in SMEP mode, then executing code in user space when the processor is in ring 0 will generate a page fault. And how this is triggered is if you take in OS, or I guess I'll go over this right now. Basically, how memory is mapped is there are these things called pages, and some of the metadata attached to the pages is basically whether or not it's in like user space or kernel space. And if the bits marked in user space and the processor is currently in ring 0, then that's how it can tell, because it can just simply check the metadata on the page. So paging. Oops. Yes. Yes. So page offset. That's not what I want. Okay, yeah. So basically at the end of the I guess the last bit is how it detects the whatchamacallit, whether or not it's in user space or not. So this happens like on the CPU. Then there's SMAP, which is basically SMMP, but for fetching data. And then there's mmap min address, which basically it's this value you supply to the kernel. You can do it at compile time, or you can also set it at runtime as well. But basically, it's so that you cannot map addresses below this address. And I'll get into why this is important in my demo, because this mitigation is how you prevent my exploit from working. But if you think about SMMP, it's basically like DEP or NX for kernel space. Because if you think about NX, it's basically you cannot execute. You can basically, if the code or some memory is writable, it should not be executable. So as the corollary for that in like for kernel exploit mitigations is if the code is in user space, it should not be executable entering 0. And who can think of a way to bypass SMEP? It's very similar to how you bypass NX or DEP in the user space. Almost exactly the same way you bypass NX in user space. Okay, well, yeah, basically it's basically you just ROP. So you think about, if you get code execution in kernel space, instead of just like mapping code in user space, like having the kernel like let's say you can control the instruction pointer when the processor is in ring 0, like when it's executing in kernel mode. Basically, instead of just like supplying an address where in user space that you've mapped all your shellcode into, you can simply look for ROP gadgets inside the kernel itself, and then just like make a fake stack like on the user space, map in a fake stack, and then just have all the instructions on that stack point to instructions in the kernel code. So basically, you just need a ROP if you want to bypass this SMAP. So going back into the mmap min address mitigation. So the main reason why it's there is because the kernel uses a lot of function pointers in its code base, and there are potential bugs where uninitialized function pointers are called. So if you can find one of these bugs, a malicious program can simply map shellcode into address 0 and simply trigger the null function pointer bug, so that way they can run arbitrary code in the kernel. So by having mmap min address, this eliminates those cases. Though it's still a bug. Like you shouldn't just call stuff. You shouldn't just call a function pointer at address 0. So yeah, that's how they do it. So how do we exploit prevent vulns? So first off, we need to find a vulnerability in the kernel that will allow us to run arbitrary code, which I'll go into in a demo shortly after these slides. These will basically look exactly the same like typical user space vulns. So there are stack overflows and whatnot. There's also some heap stuff, but the kernel has its own heap manager. So it's not like glibc. Glibc's heap and stuff. It's a bit different. Oh yeah, and aside from that, you can also have race condition. Race condition vulns are typically more common in the kernel. And after we find out vuln to get arbitrary code execution, we need to use the vuln to elevate our process's privilege level. For example, setting the UUID to 0. And basically how the kernel keeps track of this is for each process, there's a task struct associated with each process, and there's this creds structure within the task struct. And there are these functions in the kernel that you can call to change the creds, or to set the UUID to 0. And after you've done that, you can just switch back to user space, and then you have your privileged shell in ring 0. Yeah, so if you want to look at the actual Linux code base, yeah, this is the actual thread structure. And basically there's an attached struct, you can just overwrite this with the creds that will give you the the creds that you want to elevate your privileges. Yeah. So basically this function commit creds takes in this cred struct that you can supply, and it'll just set your processes creds to whatever you supply. So if you have if you call prefer creds with null, it will just give you root. It will just give you the root equivalent creds. So you can just call commit creds with prepare creds, and then that will just give you root access. So the basic structure of a CTF kernel prone problem is that there's usually a file system image, usually in a CPIO archive, and this BZ image, which is the actual kernel binary. And then there's this shell script for starting the pwnable and QEMU. So the file system image basically contains the device driver, vulnerable device driver, plus the usually Busybox and some other utils, plus the init script. So that's, and you can just look in IDA to analyze the vulnerable module. All right, so are there any questions so far before I go into the demo? No? Okay, so yeah, demo time. So this was a problem back in the last UTCTF. I'm just going to, it was a two-part problem. It was basically you had to exploit a user space binary, but the flag was running, but the flag had you had to have root access to flag. So you had to first exploit the user space binary, then exploit this vulnerable device driver that was running on the server to elevate your privileges to get the flag. So it's a two-part thing. I won't go over the first part because it's a different topic. There's standard use-based pwning, but I'll go over the whatchamacallit, the actual kernel exploitation part. So basically in the challenge, you were given these things. You were given this BZ image, which was as talked about, the kernel image file. This shell script, which is basically just calling QEMU with the image that I gave you plus the file system, and then the actual file system itself. So to actually see what's going on. Okay, so yeah, in this case it's just calling my whatchamacallit command, which we won't be going into because I don't want to show you guys how to exploit the first part. So the first thing you do when you find a kernel exploitation challenge is you just want to see what's in the file system itself. So just undo the file system using the CPIO command, and then see this init script, which is not much. It's basically just calling my pwnable with the Simplicio account, which doesn't have root access to the flag, which is here. The reason why it says this is not the flag is because I had to provide them with the file system image, and I didn't want to actually give them the flag here, so I just swapped out the flag. So yeah, we don't really need to look at the pwnable because I'm going to assume we've already exploited it. Bin's not that interesting because it's just whatchamacallit, Busybox utils that I supplied in my image. However, this whatchamacallit, this is an interesting part, which is the actual device driver. So to take a look at that, let's go into IDA.
Oh wait, it could be because I updated Pwning recently and it has to update my .NET packages. Yeah, so my IDA I think binary is a Windows binary, so I have to run it through Pwning. And I guess we can also like take a look at it through what should I call it? We can also look in GDB. This takes too long. Oh wait, oh here we go. Okay, so let's see. Let's go to the init thing. So basically, this is initializing the module, and it's basically setting up the device driver. So it's not that useful. However, this ioctl thing, this open function is basically like what's called like when you open the device driver. The only interesting thing is this ioctl function, which is what's called when you supply doing an ioctl syscall. So basically, as you can see, we have this thing called view feet picks. So there's an array of feet picks, which isn't necessary, but there are some like feet picks you can look at here. There's also this share of feet picks, which is somewhat more interesting. Let's see what it does. It's basically you're copying, I think, ODIRs. Yeah, 20 bytes from the user into this buffer on the stack here. 28. That's also interesting. However, this is the most interesting part, which is we're directly calling this func thingy. So if func is whatchamacallit, set to rbx, which could be 0. So this is set to args, which is what we supply, command, which is what we supply. So if it's this one, then we go here. If not, we
move it to here. If not, we go 0. So
R12D is basically the command that we supply. And if it's 0 to 100, then we go here. And if it's not, we go here. And we first compare it with whatchamacallit, this. And if it is, we just keep going like that. So if it's not, so the key is if we skip both of these checks, this function should still be 0. Which, if the min address thing isn't set, then you can just map something into memory at 0. You can map stuff into memory at 0. Put your shellcode there, then just trigger this bug, and it'll call your shellcode. So yeah, so that's basically what we're going to do. Oops. So I think I already have the exploit here. Wait, not this exploit. So I'm not using this. Oops. I don't know why it's. There. Okay. Yeah, so basically what we're doing here is we're opening up the device driver dev simplicio, and then we're mapping in the 0 address because we want to trigger that null function pointer. Then we're copying in shellcode, which basically allows us to which basically all it does is it calls commit creds for us, and then after that we create a new credential structure using the init creds thingy with
argument 0, and these are the addresses in the kernel binary that are the functions that we need. And the reason why I can do this is because I've disabled KS Castler, so these memory addresses will be the same on each reboot. So I can just look at it once, and then we have it. And you can view it by using the system.map thingy. Grep. All right, it's actually so we do it, but yeah, this is how you do it. So you can view the commit creds, prepare creds. And so that's how you get the instruction locations. So yeah, we need to call our octal by skipping the 0x100 and the 0x200 checks, so we just supply any other number besides 0x100 to 0x200. I just supply this number, and then because it's supplied with this argument here, I can just apply the init creds to chain it with the commit creds thing, and that should give me root access.
Why does SMEP not stop this?
SMEP does stop this.
Oh, okay. So it's disabled for this one?
Yeah. Because if you look at my command.sh, yeah, if it had SMEP, I think QEMU86 has like an SMEP
option.
Okay. Also, when we mmap null,
yeah,
doesn't that mmap it to the process virtual address null? And then when you call it from the kernel, why does it go to the same physical address, I guess?
Well, for mmap, if you whatchamacallit?
Basically, if that's a good question.
Okay, so the actual. So I think for mmap, it should actually be the address that you specify is a virtual address rather than the physical address. So going to the man page, it returns the physical address, but the physical address is in the actual physical address that it calculates. It actually maps the virtual address that you supply to. It's just dependent on the implementation.
Okay.
In which case, virtual address should still be the same when you're in kernel user space. They're just following the same like page.
Oh yeah, I see. Yeah.
Yeah. Physical address is what is returned from mmap. We supply the virtual address, which is 0. But yeah, if brought up a good point. If SVP is enabled, then this attack it would still work. You just have to do some other stuff.
You'd have to like build a blockchain.
But which shouldn't be that hard.
Can you do similar things to like ROP to mmap to like for the NX situation, you ROP to mmap to disable write so that you can now execute your shellcode? Can you do similar things in like kernel space where you?
Oh yeah, you actually can.
Okay.
Yeah, you can. Okay, so the reason why people don't do it because they only really want to do it
for one thing, which is just to like to change out the credentials, which is like 2 functions. So the blockchain shouldn't be that bad. However, you can also just like there's just a bit in CR4, I believe, or CR0, the control register that's set to check for SVP. I think it's CR4. Yeah, CR4.
Oh yeah, it's SMAP. I think SMEP is something similar as well, but SMAP is there's this bit in the control register that you can just like toggle, and if you just toggle it in kernel space, then you'll just disable like SMAP. And I'm pretty sure there's something similar for SMAP.
Okay.
Yeah. So yeah, you can just do that. So yeah, basically how you would test this is, basically I've created this. I swapped out the init thing to not run my pwnable and just like execute. Just to switch the Simplicio account and to run binsh. So if I do my command, okay, yeah, I'm in this shell, right? And I can't access root. Oh yeah, and this a.out thing is something I put this back into the file system to test it out, to show you. And the actual like CTF challenge I wrote, you basically had to you said like you can copy your binary into the file system to test it. However, to actually like exploit it against the server, you'd have to like do all that. You actually have to call it mmap like from your whatchamacallit, like either your shell or just like in your exploit that you've had in the user space binary. So
could you not write the I was gonna say, could you not write the exploit into like temp/whatever and then just call that?
Yeah, you can also do that. It's just that whatchamacallit. There's just like some weird stuff because you have to also like, because basically you'd have to like send all the
you'd have to like compile it, right?
You have to compile it. You'd have to like send it over your thingy for somehow, and you'd have to like, because you just have a shell you're just sending it to. It's
yeah,
like,
I guess it would just be inconvenient to like copy the binary to the server somehow.
Yeah. And then I just run my exploit thing, which uses, here's the here's our, what should we call it? Oh yeah, I don't have file, but I have Simplicio device driver file and /dev. So if I just call a.out, it gets the flag, which is basically what I wrote in the exploit script, was to just a cat it after I trigger the vulnerability. So yeah, that's basically relatively simple codon exploit.
Nice flag.
Yeah, thanks. I think this was 2020 spring, so that's like, wait, what was it? This is 2020.
I think this is during graphics.
Yeah. So you should take that class if you haven't taken it. Vuga's a pretty good teacher. So yeah, this is basically how you do it. Okay, also, the shell code that I have here is basically just whatchamacallit. It's you just do this.
I think it's shellcraft.sh. Right.
Yeah, well, basically what I did was I just called assemble on like this string edit. So like it was like can I not split? Okay, yeah, there we go. That's not it. System. I need to find a commit cred thing, so I just like it's just basically that. So just like calling the thingy. So yeah, that's basically it. If I were to enable SMEP, how you would do this is you'd have to find like a stack pivot gadget, and then try to pivot the stack in the kernel space to some user space stack. And you have just like rock chain full of kernel gadgets that will allow you to do the same thing, like with commit cred and stuff. And to find kernel gadgets, you just basically run rock gadget on like the kernel binary, which I've supplied here, which I think is pretty big. Yeah, it's pretty big. And it also like depends on like your kernel version as well, like different compilation options. So that's why I gave you BZ image as well, like just in case. So yeah, that's how you that's basically the kernel Pwning. Any questions? All right, cool. Yeah, that's all I have.